Okay. I'd like to welcome you all again to another installment of Quantum Fluids and Isolation. So this week we have Professor Boris Svistunov coming from UMass Amherst. Professor Svistunov got his master's degree in physics in 1983 from the Moscow Engineering Physics Institute, and his PhD in 1990 from the Kurchatov Institute in Moscow, where he worked from 1986 to 2003. In 2003, he joined the physics department at UMass Amherst, where he's now a full professor. He's also affiliated with the Wilczek Quantum Center in Shanghai, and he's a member of the Simons Collaboration. And he's also a fellow of the American Physical Society, and he's known for his work on superfluidity, supersolids, and strongly correlated systems. And today he'll be talking about space and time crystallization and multi-component superfluids. So please help me in welcoming, either by unmuting yourselves or by clapping virtually, Professor Boris Svistunov.
Thank you very much. So let me share the screen. Okay, how is everything? Do you see?
Yeah, it looks good.
Oh, okay, very good. So today I will tell you about something which is not the mainstream of my activity, which is essentially first principles approaches to strongly correlated matter. But I believe this topic is quite interesting and sort of timely, because nowadays a lot of people are talking of time crystallization, and today I will try to convince you that time and space crystallization effects are just absolutely natural for superfluids. You can ask a question, why are there multi-component superfluids? And the reason is that with single component superfluids, where we all have all these effects, there can be some observational concerns. And I will explain why. So with single component superfluids, it's basically because measuring the phase of a single component superfluid is problematic. We typically measure relative phases, while with at least two component superfluids, and I will not be going beyond two component. Moreover, I will be talking the so-called counterflow superfluid, which mathematically is absolutely equivalent to a single component superfluid. However, there will be no those subtleties with measurement. That's why multi-component. But most of my talk will be about single component superfluids. At the very end, we will see that the connection is very simple. So we do not need to start speaking of multi-component superfluids right away. Also, from the very beginning, when you see space crystallization, you might start thinking about supersolids. When we have density profiles, my talk will have absolutely nothing to do with supersolids. So our densities will be perfectly uniform in space and will all be about the phase, the space and time order, long-range order in terms of the field of the phase. Oops. So here is my collaborator, Nikolai Prokofiev, and this is the link to the paper which I will be presenting recently, a relatively recent paper. So before we'll start, it's really important to give a definition, because, you know, we really need to understand what do we mean by a crystal and a time crystal, because here I will be understanding both space and time crystallization most broadly. So I am not talking of, say, this or that particular observable, like, say, the density of matter. And it will not be important for me whether the long-range order in time and space domain comes from, say, interaction, or has nothing to do with interaction, like in an ideal Bose gas, which can behave as a classical field. So, however, I really want to give the definition. So by crystal, I will mean a state with broken translation symmetry, emergent, spatially periodic structure in terms of whatever observable. So whatever can be observed, in our case, it will be the phase, If the observable features a periodic structure in space, I will be calling it a crystal. If we have a periodic structure in time, it will be a time crystal. If we have both, it will be a space-time crystal. Actually, a superfluid is a natural time space-time crystal, if we are talking of a moving superfluid. By the way, please interrupt me and ask questions whenever you feel like asking a question. That would be perfectly okay. That's how I will be feeling your presence. Okay, so here's an example of what we can call a semantic order, or an experimental protocol revealing the semantic order in a moving Bose-Einstein condensate. So this is the famous experiment done by Wolfgang Kettel and his group back in 97, when they took two condensates into separate traps and just released them, and then the condensate were overlapping, they start interfering, and those are the interference fringes. So it's the so-called absorption image when you send a resonant light, and depending on the contrast, so dark means that the density is maximal, so almost all light is absorbed. Gray means that some portion of light is absorbed, some is not, and white just means nothing is absorbed. So you see those fringes, and this is a projection. Obviously, if you do an image, you project onto a plane. So you clearly see this periodic structure. Now, this structure is really a density modulation. But my point is that this density modulation, which we created by just having an interference of two condensates, the information about the period of the structure was already there. So it's not something which we created. We just converted the information about the broken translation symmetry in each of the two condensates due to the motion. We just converted it into the spatial modulation of density. And this is the tool to observe something which existed already in two separate condensates. By the way, it's precisely the reason why I ultimately want to discuss a two-component system, because you see, there is kind of a generic problem. Whenever you want to measure either the time crystallization effect in a moving superfluid, or excuse me, the space crystallization effect in a moving superfluid, or time crystallization, you always need two samples or something equivalent. So that's kind of, this experimental protocol is illustrative of my need for two-component superfluid to make the picture clear. And also in the context of this observation, I want to make a historic remark, which you probably will find very interesting. So quantitatively, not just qualitatively, but absolutely quantitatively, this experimental outcome can be described by the Gross-Pitayevsky equation for the condensate, for the moving condensate. It's interesting that the existence of this scalar equation describing bosons was actually predicted by Einstein in his very first famous paper. Actually, it's a series of two papers back in 1924, before actually the full-scale quantum mechanics was formulated. And this, let me just cite Einstein. One can assign a scalar wave field to such a gas, the gas of bosons. At that time, actually, people didn't know the difference between bosons and fermions. Einstein was thinking that actually this applies to any dilute gas, including a dilute gas of electrons. Quite a funny circumstance. But nowadays we understand that what Einstein was writing was actually all about bosons, dilute gas of bosons. It looks like there would be an undulatory field associated with each phenomenon of motion, just like the optical undulatory field is associated with the motion of light quanta. So essentially Einstein was predicting more or less this outcome. This piece of Einstein's paper was completely forgotten, because you see, after publishing this paper, there was an opinion that the paper is not correct. And it was only in 1938, after the Superfluidity was discovered that one of the London brothers realized that the phenomenon of condensation, nowadays we call it Bose-Einstein condensation, but I would say it's fair to say that it's Einstein's condensation because it was Einstein who predicted it, who derived it, that this phenomenon is real and relevant to superfluidity. But this nice piece of Einstein's paper about the prediction of a certain unknown at the time, then unknown scalar field, which actually is the field described by Schrödinger's equation, was completely forgotten. Okay, but this will be really important for us because yes, the discussion in terms of the classical field will be really, really important for me for making the point. It's all about the classical field behavior. By the way, the notion of a particle is the most misleading notion in the theory of superfluidity. So if you really want to understand the phenomenon of superfluidity, forget about particles. Oops, sorry. So let me see. Okay. So let me discuss a little bit the notion of time crystal in more detail, because you see, some people believe that time crystal is something which is all about just some oscillation in time. And my point here is that it's something more than an oscillation. Like our clock is ticking, whether we can call it a time crystal, and my point is no. Because you see, it's not just some periodic process. It's the process where the frequency, the distribution of frequencies, if we do the Fourier, is macroscopically narrow. Because you see, if you have some oscillation process, there is at least a phenomenon of dephasing, meaning that we have some reasonably defined period, maybe extremely well-defined period. But my point that in accordance with my definition, if a system, a macroscopic system, qualifies for a time crystal, this frequency should be defined with a macroscopic accuracy. So the uncertainty on frequency should be absolutely narrow, should just vanish in the macroscopic limit. So think of a sort of a super clock. So if you take just a standard clock, they somehow need to synchronize it, because otherwise it gets dephased and at least there is some accuracy. With what I mean by a time crystal, this accuracy should be actually controlled by macroscopic size, and it should be absolutely accurate in the macroscopic limit. So it's good to think of yet another very actually related phenomenon of Kuramoto synchronization mechanism. So Kuramoto published a series of papers dealing with purely dynamical models, not necessarily equilibrium dynamical models, but in principle, this consideration, Kuramoto's analysis, also applies to superfluids. Kuramoto's idea was just to consider a set of what he would call oscillators with a very special interaction. I would say that it's a special interaction which preserves global U1 symmetry. And what he observed is the following. So each of the oscillators can have its own frequency. Suppose you put the system in a certain random external potential, like you put your superfluid in some disordered medium. And so, however, Kuramoto's effect is the synchronization, despite the fact that the system is locally random. There is a global, well-defined, macroscopically accurate frequency. That's what I mean by the superfluid, as opposed to just something which ticks, producing some period. And the same, you see, the same logic applies to space crystal, because we use the same logic when we are talking of space crystal. For example, if we take a one-dimensional system, a system of, say, particles, atoms, classical maybe, particles at finite temperature, we do know that there are no crystals in 1D at finite temperature. The reason are just is the fluctuations. The fluctuations will actually destroy the long wave correlations. Meanwhile, locally, we will see nice oscillations, spatial oscillations of density. Just it's one-to-one correspondence between the macroscopic accuracy of the period in time and macroscopically well-defined period of a crystal. So if we go to Wikipedia and read the article about time crystals, we will learn that the idea of time crystals was formulated by Frank Wilczek pretty recently, back in 2012. We will also learn that later work developed a more precise definition of time crystals, and more importantly for our talk, that it was proven that they cannot exist in equilibrium. And this statement is actually wrong. Time crystals can exist in equilibrium, and actually superfluids are very typical, prototypical time crystals. But we will see what actually comes, what is the actual meaning of the nice theorem. People keep calling it no-go theorem, but it's not quite no-go theorem. It's just like go with care theorem. And what's also important that nowadays there is a lot of theoretical and experimental work on time crystals, but mostly, this work is mostly about driven systems. When essentially there is a periodically driven system, and when the system develops a period which is different from the period of the driving force. So that's why the work which I am presenting is not quite a mainstream of people, or what people nowadays call time crystals. So Josephson effect. Josephson effect is just the demonstration of time crystallization of in superfluids. So if you, or superconductors for that matter, you just take two superfluids or two superconductors, you apply voltage. Applying voltage is not a big deal. It's not like you introduce something which is non-equilibrium, because the Josephson link is tiny. So those two pieces, which I kept at a voltage difference, they are just two pieces of equilibrium matter, and then you see oscillations. This is the manifestation of the time crystallization. As I already mentioned, and want to reiterate, that we are talking of a super property, so that the frequency of oscillations is defined with macroscopic accuracy. It's not just some oscillation, like in a generator of frequency. It's the oscillation with absolutely accurate, macroscopically accurate frequency. And that's why there is so-called Josephson voltage standard. As we will see later, as I will remind you later, essentially the Josephson effect establishes a very strict, macroscopically accurate relationship between the frequency and voltage, or the frequency and the difference between two chemical potentials is the same. Meaning that essentially, depending on whether we have, say, an excellent standard of voltage or excellent clock, we can use this super clock, which is the Josephson setup, for either measuring the voltage with great accuracy or measuring time or frequency with great accuracy. Given the fact that we do have atomic clocks which are extremely accurate all by themselves without any kind of macroscopic effects, just a very narrow line. Given this fact, the Josephson effect is being used not as a super clock, but actually as a super voltage standard. That's why NIST essentially developed the Josephson voltage standard based on the Josephson effect. but the kind of super clock property is there. It's just the super accurate relationship between the voltage and frequency. Okay, if we look at the Wilczek's paper, so obviously Frank Wilczek did know about the Josephson effect. And let's see what he wrote in his paper. Wilczek wrote that AC Josephson effect is a semi-macroscopic oscillatory phenomenon related in spirit to time crystallization. It requires, however, a voltage difference that must be sustained externally. So it's not a ground state effect. Actually, this statement is not quite correct. And later, Frank Wilczek ultimately reconsidered, his opinion about the AC Josephson effect. So nowadays, if you listen to Frank's talks, he would present Josephson effect as a typical example of time crystallization. Because you see here, one should not confuse the finite size effect, because if your two pieces of superconductor are finite, obviously you need to sustain the voltage difference. But if the two pieces are macroscopically large, the oscillations will be forever. So kind of this voltage difference is not a driving force. So it's not like you have something driven. It's just the difference between two chemical potentials. Now we come to this very important paper, published relatively recently, a paper by Watanabe and Ashikawa. The paper claimed the absence of time crystals in any equilibrium system. And actually, a huge fraction of community believes that time crystals do not exist based on this particular paper. So what's wrong and what's correct in this paper? The derivation in this paper is absolutely correct, but what was missed by the authors, or it's better to say what was implied in this derivation, is that the energy was the only constant of motion, in which case the conclusion is absolutely correct. But if we are talking of superfluids, obviously we do know that the energy is not the only constant of motion. The amount of matter, if we are talking the language of the classical field, or the amount of particles, if we are talking the language of quantum field, for our purposes, it's just sufficient to speak the language of classical field. The amount of matter is conserved. Moreover, if we would be looking, formally speaking, for the absolute minimum of the energy, we would end up with an empty system, because the moment you add atoms that repel each other, the energy becomes positive. So obviously, if we are talking of superfluidity, say in a weakly interacting Bose gas with repulsive interaction, obviously we need to minimize our energy under the constraint that the total amount of matter is conserved. So we deal with the grand canonical ensemble, we look for the ground state with a fixed amount of matter. However, there are two very important, or twofold, if you will, implications of this novel theory. One I already mentioned, an equilibrium time crystal is supposed to have at least one extra besides the energy additive constant of motion. Another one is quite important for my talk today, and actually the reason why I really want to deal with two components rather than with single component superfluids. The observable revealing the time crystallization has to violate the conservation of this constant of motion. So while the effect is there, there is a special challenge of observing this effect. So it's not a coincidence that to observe time crystallization in a single component superfluid, we really need two superfluids. Same thing to observe the space crystallization, we need actually two pieces of Bose-Einstein condensate flowing towards each other. So this is this aspect 2 of the no-go theorem. So let me briefly introduce you to the basic theory of superfluidity, with saying that superfluid is actually a natural, the most natural low temperature state of a classical complex valued matter field. So if we really want to understand all the basic properties of a superfluid, we do not need to think of actual quantum field of bosons, or say Cooper pairing and fermionic system. It's absolutely sufficient to think of a classical complex valued matter field. We will be able to derive absolutely all general thermodynamic properties. If we are talking of a real system, which obviously is quantum, everything is quantum in our world, we just understand that if we are talking of bosons, the property of being superfluid is something which is naturally inherited by bosonic quantum counterpart of classical matter field. So if we do the standard routine of quantization of classical field, we end up with the quantum field which can inherit this purely classical field property. If we use this language for crystals, we understand that, speaking this language, a crystal, like an insulating crystal of helium-4, say, under high enough pressure, it's an essentially quantum state. So the effect of quantization leads to an insulating ground state, something far more non-trivial than a superfluid if we start with a classical field rather than in the system of classical particles. So in fermionic superfluids, the classical field behavior is emergent, but qualitatively speaking, there is no difference. So whenever we have a certain degree of freedom, which behaves as a scalar complex valued classical field, we should expect phenomena which are either directly superfluid phenomena or phenomena which are isomorphic to superfluidity, like, for example, a system of easy plane spins. So Gross-Pitaevsky equation. So here is the famous Gross-Pitaevsky equation, in a sense envisioned by Einstein. Obviously, Einstein was not thinking of this nonlinear term, but conceptually, an equation for a scalar classical field was envisioned by him. And we can ask a question, okay, but what's psi? Because we are used to think of psi as if it's a wave function. Psi is not the wave function. And in particular, the phase of psi is not something which is fundamentally unobservable. There is some challenges I already mentioned in observing the phase of psi. This is something which exists in a classical field, as opposed, say, to quantum mechanics when we write down the wave function, but there is absolutely no way we can observe its phase. Now, there are two prejudices about Gross-Pitaevsky equation. People call it essentially quantum, just because of the similarity to the Schrodinger's equation, and in particular because each term of this equation contains the Planck's constant. The moment we see the Planck's constant, we say, oh, this is something fundamentally quantum, because Planck's constant is everywhere. But wait. You see, there is Planck's constant and there is mass. And I was telling you that the most misleading notion in the theory of superfluidity is the notion of particle, and same thing happens here, because you see, if we are talking of the field, what's the mass? The mass is the mass of a single particle. And then if you look carefully at this equation, you can say, okay, with the classical field, we do not know what's the normalization. So actually we can observe Planck's constant into the normalization of our psi. Because how do we know whether we observe this or that psi We just observe something, say the mass density. So we should properly normalize our psi to the total mass density. Then we will see that actually the Planck's constant enters the other expressions in the form of a ratio, Planck's constant over the mass. And if we do not have an access to the quantum properties of our field, it will be just a ratio, h over m, which we cannot decompose into two separate pieces. So it's good to know that the origin of this equation in actual world is all about particles, but as long as we do not have an access to the quantum of corresponding field, as long as we think of psi as if it's something purely classical, qualitatively analogous, say, to classical electromagnetic field, we would never ever be able to separate h over m into the numerator and denominator, meaning that we are not going to observe h bar from the Gross-Pitaevsky equation, from any phenomenon described by Gross-Pitaevsky equation. We would need to go beyond it in terms of quantization. Same thing with actually this term. So if we look at this term, we will see that it's just some constant which we cannot decompose into the pieces. If we know quantum mechanics, if we do have an access to the details, we would see that there is Planck's constant, there is to particle scattering length, there is the mass. But if we just have an access to our equation, to the phenomena described by our equation, we would have just some constant here. There is yet another prejudice, which kind of is as dangerous or irrelevant as the quantum mechanical aspect, or even more. So people are used to think of psi as an order parameter. So whenever people see psi, they say, oh, it implies some broken symmetry, because and thus Bose-Einstein condensate, because you see psi features the phase is the indication of the broken U1 symmetry. This is the wrong idea, because you see phase is something local, but the broken symmetry is something global. So there's absolutely nothing wrong in a description of a normal phase with such an equation. We would need vortices, we would need some large enough temperature so that we do have vortices. We would need some ultraviolet regularization, because yet another property of classical fields is ultraviolet catastrophe, which would not allow us to have a finite temperature for a classical field. However, if we impose some constraint on the field, like spatial discreteness or just the absence of high enough harmonics, everything is fine with this classical field description of a normal phase, of the normal phase of bosons. Moreover, it's absolutely relevant. This description is absolutely relevant for understanding the phase transition from a superfluid to normal state in the weakly interacting Bose gas. Just absolutely accurate quantitative description. So, as I said, we can eliminate the Planck's constant from our equation, and everything will be expressed in terms of the ratio of h bar over m. If we do not have an access to quantum mechanics, we will see just this gamma. This gamma plays an important role. It's sort of unobservable, because given the fact that the velocity is proportional to the gradient of the phase, and this gamma controls the quantum of circulation of the velocity. So this is the only observable thing. And this is essentially the classical field model, which we need to understand the superfluidity. And here comes the space-time crystal. So if I take a very simple solution for my classical field, which is the plane wave. For example, I can just take the ground state, which is a uniform field without loss of generality, a real field. The phase is one and the same everywhere, and just start moving along my system. That's what I'm supposed to see. I'm supposed to see the plane wave. And this plane wave as a time crystal, because you see time-space crystal, because you see here is the phase, which is a function of coordinate with a certain wave vector. And here is the time evolution, the evolution of the phase with time. And the actual question is whether we can observe this fact. So in one of my very first slides, I was showing that while we cannot directly observe this thing, we can superimpose two plane waves with opposite k's, and then we will extract the information about the k which was there, and in principle about this guy as well. So now I want to introduce some important relation, some very important relation, which is called Bilayer-Josephson-Anderson relation. It's an absolutely general relation which applies to all superfluids because it's a thermodynamic relation. It's the equation for the time derivative of the superfluid phase. This wiggle means that it's actually a coarse-grained phase. So it's a thermodynamic quantity as opposed to something local. And the formula says that the time derivative is constant, being average of the ensemble, and is equal to mu over h bar if we are in the reference frame where the normal component is 0. And this formula implies the key thermodynamic hydrodynamic relation for the superfluid velocity. The acceleration is equal to minus gradient of mu over mass. And in particular, it implies the Josephson effect, which measures the difference of the chemical potential. At this point, you would say, oh, wait a minute, h bar is here, and I was trying to make a point that h bar is irrelevant, and in this formula we do have h bar. It's a circumstantial effect because you see in this formula we deal with the chemical potential, and the chemical potential is defined in terms of the number of particles. So it's just the chemical potential, which is yet another quantum quantity, and the ratio of the two has little to do with quantum mechanics. If we would redefine the chemical potential, if we would introduce certain mu wiggle, which is thermodynamically conjugated with something very simple, just the total mass. So rather than talking of the total number of particles, which is an essentially quantum quantity, we would be talking about the total mass corresponding to the total mass density. H bar would immediately disappear from the Bilayer-Anderson-Josephson relation. We would immediately realize that the relation itself is of a purely classical field nature, and in terms of our classical field parameter gamma and the chemical potential dy defined in the context of the total mass, we would have very simple relations free of any Planck's constant. Okay, and this relation, and corresponding over here, we would have just the difference between two chemical potentials, mu wiggle, free of any Planck's constant. And here is the loophole in the no-go theorem, because in the original paper, the no-go theorem was derived on purely quantum mechanical basis. Actually, we have a very simple, direct classical field analogy of this no-go theorem. So if we consider Hamiltonian classical field theories, and nonlinear Schrödinger is a typical example of such Hamiltonian classical field theory, when the evolution of the field is described by the Hamiltonian equation, where in the left-hand side we have I times psi dot. Psi is just the Hamiltonian complex Hamiltonian variable, and in the right-hand side we have the following variational derivative. It's an absolutely typical expression for classical Hamiltonian mechanics in terms of the complex variables, be those variables discrete complex variables of fields, we have the same expression. And the no-go theorem looks trivial in this setup, because you see the ground state is defined by the requirement that the energy, the Hamiltonian, which gives us the energy, is minimal. so that this derivative is 0. So we minimize the Hamiltonian. But if this guy is 0, then the right-hand side of this equation is 0, and there is no time evolution. And here comes the loophole, which I already mentioned, because we need to minimize not just this Hamiltonian age, because the result is just an empty system. If we minimize this way the Hamiltonian for the Gross-Pitaevsky equation, we get a trivial fact that our equilibrium psi naught is 0. So it does evolve in time, but it's just an identical 0, so kind of something very boring and irrelevant. What we really need to do, we need to find the minimal energy under the condition of conserved amount of matter. That's why we need to do the Lagrange multiplier, which actually happens to be nothing but the chemical potential. We need to minimize the Hamiltonian H prime, which is our original Hamiltonian minus mu minus total amount of matter. I use the same letter N as for the particles, because if we normalize our classical field in such a way that its norm is equal to the total number of particles, which is not a bad idea, given the fact that ultimately our classical field describes bosons, then this is the actual chemical potential without any reservation. If this N is the total mass, then it would be our new Wiggle. So whatever language we use, we do pretty much the same. And if we find, actually, it's also good to set H bar equal to 1, in which case there is no difference between what I was calling mu and mu Wiggle. And essentially, that's the bottom line. If we find such a minimum, we immediately see that there is a term with the phase which is spatially uniform. However, the phase which evolves in time, and actually this is this time evolution, which gives rise to the Josephson effect. It is this time evolution which renders our system a time crystal. But the question is whether it's easy to observe this time evolution directly, say, in a single component superfluid. So that's essentially my concern. So yes, I do have a state like a space time crystal, but how do I observe it first? And second, or whatever comes first, we can observe that the wave vector actually depends on the reference frame. Right, so if we move with the uniformly moving superfluid in our moving frame, K is 0. So is it a good idea to discuss the crystalline order, which depends on the reference frame? Well, I can say, think of any real crystal in the context of Lorentz transformation as opposed to Galilean transformation. If we do Lorentz transformation and if we observe an actual crystal, say sodium chloride, from a moving frame, fast-moving frame, I must add, there will be Lorentz contraction, so there will be essentially pretty much similar phenomenon of crystal period that depends on the motion of our reference frame or the motion of our system with respect to our reference frame, but still it's not something quite maybe elegant if the wave vector just vanishes in a certain reference frame. And also the problem with measuring the phase, so it's quite a fundamental problem. So we can say, oh, is it easy to measure this phase? It's actually not, because you see the point is that the chemical potential depends on the convention about the rest energy of non-interacting system. So there is always a convention in how we define the chemical potential. For example, in our non-relativistic physics, we believe that the energy of a particle at rest is 0. Meanwhile, if we go relativistic, there is the rest energy, mc squared. So you see, there is a convention. Along similar lines, we can add a uniform external potential which is essentially unobservable if we just deal with the system itself. And this will naturally shift our chemical potential. And that was one of the arguments actually mentioned in this no-go theorem paper against superfluids being time crystals, just this arbitrariness of how we define the chemical potential of a system. Oops, sorry. And here comes the system of two-component superfluids. Now think of a system which has two components. In this system, we can speak of the relative phase between two components, A and B. And all of a sudden, everything becomes absolute rather than relevant, because the phase itself is a relevant quantity. So if we have a two-component system where the amount of matter of each component is conserved, and if we are interested in the relative phase, the phase difference between two phases, then the very same bilayer-Josephson-Anderson relation now deals for the relative phase, deals with the difference of the chemical potential, which is an absolute quantity. Moreover, if we do the Galilean transformation for the relative phase rather than for the absolute, each of the two phases, and if the parameters gamma, which I introduced, h bar over mass, if we derive our classical field from its quantum mechanical counterpart, if those two gammas are equal to each other, it turns out that the wave vector now does not depend on the reference frame, because you see this relative phase is all about relative motion, the relative velocity, and the relative velocity as opposed to the absolute velocity does not depend on the reference frame. So all of a sudden, everything becomes absolute rather than relative, and that was the only reason I wanted to talk of the two-component systems. And here comes a setup. I will just introduce two setups. One will be a condensed matter setup, and another one will be a setup dealing with ultra-cold atoms. I would be interested in so-called counterflow superfluid, when the only superfluid mode corresponds to the relative motion of two superfluids. And here it's the right time to recall about the no-go theorem, because the actual meaning of the no-go theorem is the following. So while we do have the space and time crystallization effects, the way how we measure them should necessarily involve the breakdown of corresponding constant of motion. In our case, it means that we inevitably need the processes of interconversion between two components. So while the state itself does not have processes of interconverting one component into another, the measuring protocol should involve such processes. And here is the device based on two-dimensional superconductors. So it's essentially two superconducting films. So academically speaking, at any finite temperature, a two-dimensional superconductor does not exist, because the vortices have finite energy and the state is normal. However, what does exist is the counterflow mode. It was predicted by Yegor Babayev quite some time ago. So because you see, with respect to the counterflow, the vortices with finite energy, which destroy the actual current, they do not destroy the supercurrent, as you can easily check. And this neutral mode, neutral because you see the electric currents move in two opposite directions. If this current moves in the upper piece goes to the right, in the lower piece goes to the left, So the net electric current is 0, but we do have currents in each of the two planes. And now if we have those two Josephson links, so those red dots are Josephson links. They are tiny, so they do not destroy the equilibrium in each of the two systems. Those two links will be sensitive to both space and time crystallization effects. So in terms of the time domain, it will be just the standard AC Josephson effect, while in the spatial domain, if we have a wave vector corresponding to this counterflow, the net Josephson current will be reminiscent of what we see when we do squids. So in the squids, we do measure the phase difference between two Josephson links, and the same idea is at work here. So we have a certain wave vector, we have a certain distance between two links, and this guy, the amplitude of the net Josephson current, so the current will be oscillating, and that's how we would see time crystallization, but also its amplitude would depend on the wave vector of the counterflow. That's one setup. And let me briefly mention yet another setup, a very different setup, which deals with the superfluidity of two-component bosons. Actually, I am talking of the special regime when we have two components of bosons on an optical lattice. This system is perfectly described by a two-component bosonic Hubbard model, and the only requirement is that the net density, the sum, the occupation number, the sum of the occupation numbers is commensurate, either 1 or 2, some integer, call it 1, and we need strong enough interaction so that with respect to the net flow, we have Mott physics. So Mott physics does not allow us to have the net flow, but we can have a counterflow. And this counterflow, it's precisely what we need. It's pretty much the same setup which we discussed before. So the relative phase is well defined, and we have the same physics. So I have a slide with the experimental protocol. It's pretty long, and I'm not going to describe all the details, but what I want to tell you is the following. So what's good about ultra-cold atoms, you do not need to have your Josephson links all the time. You can just apply two pulses, two interconversion pulses, one pulse, local interconversion pulses, if you want to see not just the time crystallization, but also the space crystallization effect. So the two pulses, interconvergent pulses, which convert the atom of component A into the atom of component B, and this is possible with ultra-cold atoms. So the beauty of ultra-cold atoms that you have internal degrees of freedom which allow us to do that, because obviously if we take some kind of two-component system consisting of quite different particles, there is no way we can convert one type of particles into the other. So once again, this subtlety implied by the no-go theorem is is not relevant for ultra-cold atoms, because we just have systems with internal degrees of freedom, and we can apply interconvergent pulses. So if there is space-time separation of these pulses, we apply them, and what do we need to observe? So the observable is pretty non-trivial. So we really need to count atoms. So yet another option which we have with ultra-cold atoms, after performing the experiment, we can apply an optical lattice. We can do single-site microscopy, and we can literally count each atom in each of the two components. And if we repeat this experiment quite a number of times, the noise, the fluctuations of the difference of the number of particles will be sensitive to the space-time separation between our pulses. And essentially, that's the end of my talk. Two very simple take-home conclusions are the following. Superfluids naturally feature the effects of space and time crystallization. And with counterflow superfluids, which are just isomorphic to single component superfluids, those effects are conceptually much more straightforward. Thank you very much.
Okay, if anybody has any questions, they can please feel free to unmute yourselves.
Hey, Boris, you mentioned it briefly, but in regards to the Josephson effect, where you say that the appearance of H bar is somehow not indicative of quantum behavior, can you just explain that argument again? I think I missed the.
Okay, so let me then start sharing the screen once again. So let me see. Do you see my screen actually?
Yeah, we can see it.
Oh, then I just need to, let me see.
I understood the argument in terms of the Gross-Pedievsky, but when it comes back in the Josephson relation, so how would you argue that its appearance?
Okay, got it. We're moving there. Josephson relation. Okay.
Yeah, Pierre.
So you see, it's pretty much the same argument. If you understand it in terms of the Gross-Pedievsky, it's pretty much the same argument, and you can still use the Gross-Pedievsky equation, because in Gross-Pedievsky we had a ratio of two quantum quantities, each of which is quantum, but the ratio is not. So h bar over m produces gamma, right?
Mm-hmm.
And the gamma is not quantum. Here we have the same. H bar over mu, just mu is essentially quantum. Probably you're confused with the fact that even for classical particles, we can introduce mu, right?
Right, okay, so
the point is that the moment you are talking of particles from the point of view of classical field, you are extremely quantum. So if you have a system of classical particles, from the point of view of your classical field, it's something fundamentally quantum.
Okay.
That's the point. Okay. So you're not supposed
to treat mu in a think about mu in a different way here.
Yes, and the way is very simple. Just if you divide mu by mass, which would just correspond, because you see, mu is something attached to particles, mass is something attached to particles, you get mu wiggle, which actually now is not attached to particles, it's attached to the mass density. Be their mass density quantized or not is absolutely irrelevant, and that's your final result. So this gamma, which speaking generally has nothing to do with quantization of the field, and this mu wiggle, which also has nothing to do with the quantization of the field. So if I introduce the chemical potential, which is thermodynamically conjugated to the total mass rather than total number of particles, it's a purely classical, but a purely classical field, not to be confused with classical particle, something. You see, there is always a confusion, because whatever we call quantum from the point of particles is absolutely classical from the point of view of field. Just think of the photons. What's quantum about electromagnetic field? It's not the set of Maxwell's equations, correct? It's just the fact that the electromagnetic field consists of quanta.
Sure.
That's what we call quantum. But in terms of the quantum fields, somehow it's other way around. We used to think of particles as if they're classical. And that was, by the way, Einstein's original idea, that there is no difference between electromagnetic field, and he believed that all actually systems are bosons, and it's any generic system. So any system with large occupation numbers, according to Einstein, would behave like a classical field. And, yeah.
Thank you.
Any other questions?
I have kind of a general question that your arguments kind of reminded me of. It's this article by Leggett back in 1970, Can a Solid Be a Superfluid, where he talks about a single component superfluid. You put it in an annulus and you kind of rotate it at a constant velocity. And he gives this argument that you can get a super solid, or like actual density modulations. So it's what, and he, relates this to the boundary conditions of the superfluid and the container enclosing the superfluid. So this is a single component superfluid, and so I want to know if you had kind of,
So let's be accurate.
Yeah.
Let's be accurate, because in the very beginning of my talk, I was saying that I'm not discussing supersolids, because supersolids are all about density modulation.
Mm-hmm.
Here I am talking about phase being a function of position.
Yeah.
So supersolids is yet another type of superfluid systems with broken translation symmetry. They are crystals, but I'm not talking of super solidity here. Super solids are nice and good, but this is not what I was discussing today.
Okay. I guess my question is, like, he makes the same argument kind of thinking about phase differences.
Then probably I need to read Leggett's paper, because from the top of my head, I do not remember this argument. I must admit.
For sure. Okay, thank you.
Okay, any other questions? Okay, maybe we'll thank Professor Svistunov again.
Thank you very much.